The next topic we're going to cover is something called a reentrant lock. And I'll first start by talking about the concept of mutual exclusion, which occurs commonly in concurrent programs. And then we'll talk later in the next section about how Java's reentrant lock implements mutual exclusion. So what is mutual exclusion? So mutual exclusion, or mutual exclusion locks, often called mutexes for mutual exclusion, are used to define so-called critical sections. So here's a critical section. And the main property of a critical section is only one thread at a time can actually be executing code inside of the critical section. So let's imagine some thread comes along and it wants to run some code in the critical section. So the way it works is we have a lock, which you can kind of think of as like a door with a lock on it. And so if there's nobody else in the critical section, the thread that comes along next to acquire the lock can be let into the critical section. And once it's in the critical section, then the critical section is locked. Nothing else can get in. And so then the thread can go ahead and run and do its stuff and access the shared resources like fields, mutable shared state, and so on inside the critical section. During the time that that thread is in there with the critical section locked or the lock acquired, any other threads that come along are kept at bay so that they don't get into the critical section and somehow corrupt the state by setting and getting the state via multiple concurrent operations. So we only want one thing taking place at a time. That's the basic idea. And everybody else just has to wait. And they might spin, they might sleep. We don't worry about that too much at this point. Obviously, if you don't do this, if you're not careful, you can end up with race conditions because multiple threads will be running inside the critical section and setting and getting the fields, and chaos and insanity will break out. All right, so we talked about race conditions before. They basically occur when your program depends on the order of the timing of the operations for it to operate correctly. When a thread is finished with its stuff in the critical section, it can then leave, and that will have the effect of releasing the lock. And once you release the lock, then one of the waiter threads, doesn't really matter which one, unless you choose fair semantics, will get a chance to come in and acquire the lock and do their thing. OK, so that's the basic gist of how things work. So once you get the lock, you can start to run. Everybody else still has to wait. Typically, mutexes are implemented in hardware via atomic operations. That's for simple mutexes, like a non-recursive mutex. That is definitely implemented with a hardware instruction on most modern platforms. There's also more powerful forms of mutexes, such as a reentrant lock, as we'll see, which require a little software along with the hardware. And we'll see why that's the case. So as you recall, atomic operations either occur or don't occur. And typical, this is implemented using spin locks, as we've seen with concurrent swap operations. And that's what Java provides, concurrent swap methods in the Java unsafe class. You got a little taste of that with the last programming assignment. We also covered that when we discussed atomic Boolean, atomic reference, atomic integer, atomic long, all the atomic classes and operations. What's an example of a human known use of this? My favorite example is the airplane restroom protocol, which works like this. You have a little sign that says vacant. So if you come along and the sign says vacant, then you can acquire the lock. And you go in, and when you shut the door, you lock it. Now it's occupied. If anybody shows up who wants to use the restroom while it's occupied, they have to queue and wait. And sometimes the crew will yell at you and say, you can't queue at the front of the plane, blah, 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 right? But you're still queuing somewhere. You may have to go to the back of the plane. When you finish, then that changes the state from occupied back to vacant. And at that point, someone else can come in because the lock is available to be acquired. This illustrates the concept of fully bracketing. The person or thread who locks must be the same person or thread who unlocks. So that's fully bracketed in this context. All right, so that's just a quick overview. That makes it easy to remember what a mutex does. So now that we've given an overview of the concept of a mutex, let's start to be more concrete with how Java implements mutexes via reentrant locks. So what's a reentrant lock? Well, a reentrant lock is an implementation of the concept of mutual exclusion used for concurrent Java programs. So here's the documentation for it. If you were to take a look at the implementation, you'd see that it's a class that implements something called lock. I'll tell you more about that in a second. And it's also something that's so-called serializable. The lock interface is something that is used for several different synchronizers in Java, including reentrant read-write lock, and it's also used for ReentrantLock. And it's super simple. It has like just a handful of methods: lock, try lock, and unlock, and maybe a couple other variants with timeouts and so on. But it's a very simple interface. And that's what it looks like. It's actually pretty fun to read the documentation for the interface of lock, because it gives you some good insights as to how it works. The implementation of ReentrantLock implements the lock interface and applies the bridge pattern. So remember the bridge pattern, the gang of four bridge pattern, basically separates the interface from the implementation, so the two can vary independently. This is a variant of the bridge pattern where the interface doesn't really change, right? We have the, and by the way, when I use the word interface, I don't mean Java interface, I mean API. So we have ReentrantLock API, which has methods like lock, unlock, and so on. And then the ReentrantLock object stores a reference to something called the sync hierarchy, which, as we saw before, very much like for semaphores, can either be fair or non-fair. And the reason we use the bridge pattern is to make it easy to support multiple things within the same uniform interface. So it just makes the code cleaner. Here's how this works. We have a final field called sync of type sync, just to be somewhat confusing. Thank goodness Java is case sensitive. And then under the hood, you can see here that the sync class extends abstract queued synchronizer, which is this framework that is used to wait for things to change, that waits for integers to change their value in a FIFO way. So it uses FIFO wait queues, and it allows you to synchronize on things. In this case, what we're synchronizing on will be the changing of the mutex's state from acquired to not acquired. There's a constructor, a couple constructors actually. One of the constructors takes a Boolean that indicates whether to use fair or non-fair sync semantics. And this is almost identical to what we talked about with the Java semaphore example, because they're following the same pattern, of course. And the way it works is if you give it a parameter, then the appropriate thing will be selected in the constructor. So if you give it fair, then you'll have fair sync, and that means you'll have strict FIFO ordering with no barging, and that enhances fairness at the expense of performance, because it may be a little slower to run, quite frankly. And we'll talk about why shortly. Conversely, if you choose the non-fair sync version, then it'll run faster, but you won't be fair. So the same thread may keep reacquiring the lock while others wait, which could make some problems, make some certain things hard to deal with. The default behavior, if you don't specify the constructor that takes a parameter, is to use non-fair sync. So what it's saying there is I want to optimize for performance over fairness, which is a common thing to do in the computing world. Maybe not the most common thing to do in the political world, but in the computing world, we want to be fast. We don't really care if every thread gets a chance to run necessarily. Fair sync is generally much slower than non-fair sync, so be careful when you use it. There are times when you need it, but you don't need it all the time. So the ReentrantLock is actually very similar to the monitor lock that's provided by Java's built-in monitor objects. And we'll come back and talk about this later. There's some videos on my website you can look at if you want a preview of that. But for now, the main thing to remember is that synchronized statements and methods use what's called the monitor lock, or the intrinsic lock, as it's often called. And those features for the intrinsic lock, for the monitor lock, are like lock and unlock methods on ReentrantLock. So they basically acquire the lock, blocking if necessary, and unlock releases the lock. Okay, so far so good. There's also a bunch of other things that ReentrantLock adds as well. So it has the ability, for example, to lock things interruptibly. So when you call lock, lock is going to wait, and even if an interrupt request is made, it's going to be ignored. The system will say, the heck with you, I'm waiting till I get my lock. Conversely, if you use lock interruptibly, if the interrupt flag is set, then that will cause the thread to return, even if it hasn't got the lock yet. It'll throw an exception, which is basically the interrupted exception. There's also a couple of non-blocking methods, try lock that doesn't take a timeout, and try lock that does take a timeout. And note that none of Java's synchronized methods or statements are non-blocking. They always block until they get the lock, and they can't be interrupted. So that starts to give you a sense of why people increasingly don't use synchronized statements and methods in Java, but instead prefer to use the ReentrantLock because it's more powerful and gives you more features and more options for flexible and responsive code. The other thing that ReentrantLock does is it supports so-called recursive mutex semantics. And this should be familiar to those of you who did the grad student version of the spin lock, because we implemented a recursive spin lock, a reentrant spin lock. And here's basically the idea. This is something, if you look up reentrant mutex, you'll see what it does. So what happens is, in addition to keeping track of whether we're locked or not, we also keep track of whether, or what our count is. And we start out with a count at 0. It's called the hold count, or the owner count. And when you lock, the count goes up by 1. And the way it works is that the thread that holds the mutex, or holds the lock, can reacquire it without deadlocking on itself. If you don't have reentrant semantics, it'll deadlock on itself if you try to reacquire it, because it's already locked, right? And you have to wait, and you already hold it. So that would be confusing and error-prone. So what happens is, whenever you try to reacquire the lock again, it simply increments the hold count, if you are the owner. If you're not the owner, then you have to wait. But if you are the owner of the lock already, and we know that because we keep track of the owner, then all that you do, if you are the owner, is you just increment the hold count by 1. And of course, that's done atomically, right? So that's, you don't have to worry about race conditions there, because you own the lock, right? So basically, recursive mutexes add more overhead, because you have to do things outside of the hardware. You have to keep a count, you have to increment the count. But they also provide you with more powerful semantics, because you don't deadlock on yourself. And they're particularly useful in things like object-oriented frameworks that require a lot of callbacks. So often it's the case that you call into a framework, the framework grabs a lock, the framework does some stuff, it calls back as a callback to code provided by the user. That code may have to come back in the framework, and by using reentrant locks, you're able to make sure that calling back into a framework that holds a lock doesn't deadlock. So that's a very common place in which reentrant locks are used. Let's talk about some of the key methods in reentrant lock. So not surprisingly, they're going to be things that are inherited or implemented from lock. These are the key methods. These methods are all defined in the lock interface. And as you'll see, all the methods just forward to the sync object. Remember, this is the bridge pattern, of course. So they simply forward to the methods that are implemented, or rather inherited. It's implemented by and inherited from the abstract queued synchronizer framework, with a few exceptions where they override stuff and do some other magic. So lock is very simple. It just basically acquires the lock if it's available. If it's not available, it just waits, kind of goes and spins a little bit, and then probably parks itself pretty fast. Now, what happens when the lock is not available depends on the fairness policy. So there's different things that happen in the implementation. And if we have some time later, I'll show you the code. It's really cool. Non-fair implementations of lock are optimized in hardware. They do some stuff. They may try to spin a little bit or not. You know, it kind of depends on the implementation, but there are different ways to do it. Fair implementations will park themselves on a wait queue. And that's because they put themselves at the end of the line and they wait for the other stuff ahead of them to be done. And that's because fair implementations have to maintain FIFO order. So they're parked in a FIFO manner. So the latest one goes at the end. Lock interruptably acquires a lock unless it's interrupted. We'll talk more about interrupts later, but in a nutshell, it's going to allow itself to have the interrupted exception thrown. You can see that's the exception that's thrown if the lock is interrupted. And that's nice if you want more responsive programs. In contrast, the lock method is not interruptible. So that behaves just like the synchronized statement or method in the built-in monitor objects, where it'll just wait indefinitely and cannot be interrupted. Try lock tries to acquire a lock only if it's not already held. So if it's not held, it'll get it right away and return. If it is already held by some other thread, then try lock will return false. And oddly enough, irrespective of the policy as to whether it's fair or non-fair, try lock, if you do the untimed version, does not honor the fairness setting. So it can barge ahead of other things, which is more about implementation efficiency than semantic consistency. When you call unlock, it attempts to release the lock. And the reason I say attempts to release the lock is if you don't own the lock and you try to release it, then an exception is going to be thrown. So you get an exception, a runtime exception is thrown in that case. And the reason for that is that ReentrantLock is intended to be used in a fully bracketed way. But rather than just sort of failing silently, if you try to release a lock you don't own, you should get the interrupted, you should get an exception. It's probably some invalid state exception or illegal state exception is my guess. Okay, there's a bunch of other methods. I'll go through them quickly. They're less common to use. These methods go way above and beyond what you can get out of Java's synchronized statements and methods. One thing you can do is a timed try lock, which will wait up to a certain amount of time before giving up if it can't get the lock. And this code does, in fact, honor fairness, so it can't barge. Again, somewhat curious semantics, but that's the way it goes. There's a method called isFair that returns true whether the lock is fair or not. Just looks at the status that you set when you made the constructor in the first place. There's a method called isLocked, which returns true if the lock is held by another thread. I strongly discourage you from ever using isLocked. And the reason for that is the result it gives you back really doesn't mean a whole lot, because between the point when you check to see if the lock is held and the time you get the result back, the lock status may have changed. It may be released by that point, because that's the fundamental non-determinism aspect of concurrent programming. So you're always, it's always a bit mysterious exactly what's happening. So any kind of question you ask in a concurrent program is almost always a hint, and probably wrong, right? It's doing its best to explain things, but it just can't help it because things are changing underneath the hood. There's also a very important factor method we'll come back and talk about later when we start talking about condition objects. And this is a way of making a condition object that is associated with this particular lock. And so this is basically a factory method. And don't worry about that too much. We'll come up and talk about that when we talk about condition objects. Yeah, Sri. Yeah. The question is, do we need a counter? Who's we? So yes, the Java ReentrantLock has a counter. And the counter is there in order to be able to do the appropriate thing when you call lock if you already hold the lock. And the reason you need a counter is because you need to be able to do the equivalent number of unlocks as locks. Otherwise, the first time you called unlock, no matter how many times you called lock, it would just release it, which would be really confusing. So you need to do matching. Remember, these are fully bracketed. So every time you acquire, you also have to release. And you have to release the same number of times that you acquired. And that's why we need a counter. If you can think of a way of doing recursive lock semantics without using a counter, you'll make a lot of money somewhere. There's probably a place to get lots of money for shaving off nanoseconds on ReentrantLocks. Okay, any other questions about ReentrantLock?